Well, I have explained this article before, but because this article is super important, I explain it more than once. So this is the weekly supervised question answering article that I've explained in my playlist for expectation maximization for NLP tasks. So you see that sometimes we have the answer, but we want to make it more interpretable. So there are some spans in the solution. For example, which composer did pianist marrying? We know the answer is Robert Schumann. We know the answer, but we want to also know the precise location of that in order to make artificial intelligence more interpretable, because we want to avoid imitation and we want everything to be explainable. So we model the set of possible solutions as a discrete latent variable and develop a learning strategy that uses hard expectation maximization style parameter updates. So another type of question answering is reading comprehension with discrete reasoning. For example, we know the answer is 4, but is it in a different spans? For example, 41 minus 37 or 41 minus this 37. We have different 37, or is it 40 minus 36? So we should know that, because in this way we understand that our AI is understanding it instead of just imitation and copying numbers and making. So although the difference between all of them are 4, but we want to make sure that it has understood why it has selected. So why is important. So we have different data sets for question answering. For example, in reading comprehension, we use SQuAD dataset or news or other data sets. For open domain question answering, we use these data sets. And so each data set is focused on a different purpose. So we have different tasks, as I said, multi-mention reading comprehension with discrete reasoning and semantic parsing. We model the set of possible solutions as a discrete latent variable and develop a learning strategy that uses hard expectation maximization style. So my playlist for expectation maximization for NLP task is really important for future development of natural language, because natural language has lots of ambiguities. You cannot just model it with end-to-end LSTMs and those things, because we need to add more structure to that. So it's a kind of structural learning. So we use weekly supervised question answering tasks. It is possible to formulate a wide range of weekly supervised question answering tasks as discrete latent variable learning problems. The learning challenge is then to determine which solution in the set is the correct one, while estimating a complete question answering model. We model a set of possible solutions as a discrete latent variable. So a hard EM, for example, she's talking, and we know that, so in this kind of learning, either no labels are given, it's unsupervised, or labels are given for only a small fraction of data, it's semi-supervised. Or incomplete labels, for example, the alignment between the words and the sounds of what she's saying is not given. So we have some caption and the alignment is not given. So so in any NLP task, it is important to see what is the natural latent variable that we can take advantage in order to simplify the problem. So as you know, in expectation maximization, the first step is to focus on understanding and modeling the latent variable. And once we fix that, once we understand and fix the latent variable, we can go to the next step, which is the maximization step, talking about how can we learn the parameter theta. And the parameter theta is different from our latent variable z. So there are two approaches, either soft approach or hard approach. And in the hard approach, we initialize parameters randomly, and the expectation we hallucinate some data, set the latent variables to the values, as I said, that maximizes the likelihood. In the maximization step, we set the parameters to the values that maximizes likelihood. A good example is always this Bernoulli of mixtures. For example, we know that x is just a pixel level. Is either blue or white, blue or white. So at the pixel level, we can represent this image, x. So we have the binary variable controlled by the average. So we want to maximize the likelihood. We know the expectation and the covariance. But sometimes, and of course this is the mixture version of that, mixtures of these Gaussian distributions in this three-dimensional or high-dimensional space. So we have a mixture of them, but sometimes we have a latent variable. For example, it could be anything, but the latent spatial smoothing level for an image could be considered as your z, latent variable. So the probability of your latent variable given that this pi, is this. So the objective function is crystal clear. And it is obvious for Bernoulli mixtures, it's explicit. Sorry. And so I skipped this slide to avoid distraction. So the goal is learning a model parameters which takes an input x and output a solution. You know, we have lots of spans that are the solutions. For example, this one. But we want to make sure that we are choosing the correct answer. As you know, in graphical models, you have, for example, z, we have x and y. So we have this relation between the input x and answer to the question, which is y. And we just use this simple probability rule. But here we are using this because all of the finite set of possible solutions are z total, and we know that the answer, the probability of y given zi is 1, because we know these are responsible for the output solution. That's why it is simplified through this, and we are maximizing the likelihood or minimizing the negative likelihood. And the hard EM, so in the first step, we focus on latent variable z in order to find it, to model it. And then we fix it, and after that, it's just this conventional, it's just a standard supervised learning. So in multi-mention reading comprehension, we have multi-mentions. This one, Robert Schumann, you see it everywhere, but we want to know among all spans. For example, this is one span, this is another span. Among all of these spans, so these are ZT total spans, we want to know among all of these spans, it's just a subset of that, which is spans that match Robert Schumann. And here we want, and all the spans we model it just using the start and end of that span, then we can model it